Welcome to Coach Silver's podcast on waves. To begin this presentation, you should have your behavior of wave notes printed out and in front of you ready to go. A wave is any repeating back and forth motion about an equilibrium point. Waves do not actually transfer matter. It's a transfer of energy, a transfer of a disturbance. And waves are responsible for many things in your everyday life, and an understanding of waves can open up a whole new world to how you see, the world. So let's take a look at waves in more detail here. Our discussion of waves begins with a pendulum, because a pendulum has a lot in common with how waves work. First off, the time it takes a pendulum to make one complete cycle, meaning it goes out, comes all the way back, is called a period. And it was figured out a long time ago by Galileo that the period of a pendulum depends only on the length of the string of the pendulum and the acceleration due to gravity. The mass at the end of the pendulum, ignoring air resistance, does not affect the period of the pendulum. And the relationship is the longer the pendulum, the longer the swing. The shorter the pendulum, the shorter the string. You can see this in nature with things that have longer legs have a slower gait than things with shorter legs, such as the giraffe running alongside a hamster or a mouse or a chihuahua. The giraffe's going to have a much slower gait. This also relates back to rotational inertia. If there's a longer pendulum, the mass is farther away from the center of rotation, therefore greater rotational inertia. Isn't that lovely how the different topics from different units still tie together? Physics is a great thing. All right, now more on the wave basics. If you were to sketch out a wave, it would make a sine curve as represented here. This could be a pendulum back and forth as a piece of paper is dragged underneath it. This could be a representation of ocean waves, could be a representation of anything that can be turned into a waveform. Some wave basics are stated here and in this diagram. Now, if you find any point on a wave, and you go from that point over to the identical point when the wave comes back up. So here we're going down and back. If that were a pendulum, it would be out and in. So this is called a wavelength. Now, you could take the wavelength from there. You could also find the wavelength at any point if you go back to the corresponding point when the wave comes back around. So I could go from here in blue, out, back in, and that is also a wavelength. And you'll notice that blue line is the same length as the red line. That's another wavelength. Another measure on the wave is called amplitude, which is how far away from the equilibrium or center line the wave goes. And the amplitude is related to, with sound, it's related to the volume. So here, the amplitude is from the center point to the crest, which is what this is called, or trough of the wave, which is the bottom part. So you have crests and troughs. The crests are the high parts, the troughs are the low parts. But more importantly is that you understand wavelength and amplitude here. Another property of waves that's important is frequency, and that is how many waves go by in a certain amount of time. Frequency is measured in units called hertz, and we write that like this, Hz. So frequency is not how fast the wave is moving through space, but how many times the wave vibrates in a certain amount of time. Okay, so let's look at it this way. If you have one wave go by in a second, it's 1 cycle per second. 2 waves go by, 2 cycles per second. Instead of cycles per second, we say hertz. So we already talked about a period. I'm going to use a P to represent a period. The period of a wave is equal to how many seconds. So I'm going to put a T for time in seconds. How much time it takes in seconds for the wave to do one complete cycle. And the way we measure frequency, represented by F, that's equal to how many cycles the wave does in a certain amount of time, measured in seconds. How many cycles per second? Well, these are the reciprocals of each other. So we can also write that the frequency of a wave is equal to 1 over the period of it. And the period of a wave is equal to 1 over the frequency. What that means is that period is how long it takes to do a cycle. Frequency is how many cycles it can do in a second. So this is something that might require a little more time, looking at your notes, looking at the book, playing around with it, trying to do some questions. But frequency and period are inverses of each other, reciprocals of each other. So next time you're in the car with your buddies jamming to the radio, you can talk to them about how many times the wave generating that signal to the radio is actually vibrating each second. And they will be amazed at your knowledge of waves. Something else that is very important to understand is that waves do not transmit matter, they transmit energy. This rope being jiggled by this dude's hand, the rope is not actually moving toward the wall. Energy is moving. The rope is just moving up and down while the energy is traveling along the rope. So waves do not transfer matter, they transfer energy. Again, it's not the actual water molecules that are moving out away from the splash in this picture. It's energy. The water molecules are bobbing up and down as the energy wave is moving out. Right, now, wave speed is something completely different from frequency. Frequency, how many waves go by in a second. So if you have 5 waves go by in 1 second, it's 5 hertz. You have 10 waves go by, it's 10 hertz. But that doesn't say anything about how fast the wave's actually moving through time. 5 waves passing you in 10 seconds that are very short waves, that's going to be something that moves at a different speed than 5 waves moving by you in 10 seconds if the waves are really fast. So let's look at what I'm talking about here. If you have 1 wave passing this bird every second, then the frequency is 1 hertz. But let's change these numbers a little bit. Let's say that the wavelength is 3 meters instead of 1. And let's say that instead of 1 passing every second, 2 waves pass by every second. So the frequency is 2 hertz. But what about how fast that wave is actually moving? So I've got wavelengths of 3 meters every second, 2 waves pass by. So now I've got 3 meters per wave, and every second I'm getting 2 of these 3 meter waves to pass. So 2 of these 3 meter wavelengths. So as you can see, we just multiply. I've got 3 meter long waves. I multiply them by how many pass in a certain amount of time, a second. That tells me the wave speed is actually going to be 6 meters per second. And here's our example here. And this box is not supposed to be there. This formula is supposed to be that the wave speed, how fast the disturbance or energy is actually moving, is equal to the wavelength, represented here by lambda, multiplied by the frequency. So the wave speed is equal to wavelength multiplied by frequency. How many waves pass by in a certain amount of time multiplied by how long each wave is, and that gives you the wave speed. This slide just shows you some different sounds, and it shows you the wavelength of different sounds. Now, something about sound is when it travels through the air, the speed of a sound wave is always 340 meters a second. If the sound has a higher frequency, meaning it's going to have a higher pitch sound would have a higher frequency, its wavelength is shorter. If a sound is a nice low sound, it's going to have a bigger wavelength. and what those come out to be when you multiply them together is always going to be 340 when the sound's traveling in air. Now, there are two main types of waves we're going to discuss here, and that is the longitudinal wave and the transverse wave. Transverse waves are where the medium, in this case this girl is playing with a slinky, this is an easy way to see these. In a transverse wave, the wave medium, the thing that is actually vibrating, is moving perpendicular to the motion of the wave. That's example A. Example B is an example of a longitudinal wave, which is where the motion of the medium is along the same direction as the motion of the wave. It's vibrating back and forth, and the slinky is moving from her to the wall. So A is a transverse wave, though the medium moves perpendicular to the motion of the wave, and B is a longitudinal wave. The medium is moving in the same direction, vibrating back and forth as the direction the wave is moving. Now, waves can interfere with each other. They can be what's called in phase or out of phase, and that can lead to changes in the waves, as we're going to see in this next slide. In what's called constructive interference, two waves of the same frequency and amplitude and wavelength can combine to form another wave that is the same frequency but has in the same wavelength but can have a bigger amplitude, a greater amplitude, such as in example A. In example B, you have two waves that are exactly out of phase, is what this is called, and the average of those, if you put them right on top of each other, is going to be just a straight line down the middle. This is the idea behind noise cancellation. This is called destructive interference. And again, we call this in phase or out of phase. If two waves are out of phase, the crests of one overlap the troughs of the other, and the amplitude drops to zero. And when the crests overlap with other crests, it makes a wave with a greater amplitude. Now, a standing wave is one where the wave that you send in is exactly out of phase to the one coming back. The wave going in is called the incident wave, and the wave coming back is called the reflected wave. And this forms a standing wave where the wave does not appear to be moving. It just appears to be moving from point A to point B. It just appears to be going back and forth while certain points of it stay still. This next slide is going to make that a little easier to grasp. So here we have somebody making a standing wave, and the points where the wave appears not to be moving are called nodes. And this is formed when the incident wave, the wave going in, is exactly out of phase with the reflected wave coming back, and it causes a standing wave. This is the principle behind many musical instruments, guitars, clarinets. A standing wave is created either in a string or in a column of air in a tube that creates the sound, and the sound can be changed by the length of the standing wave and how many nodes it has. This slide here just shows that if the standing wave is the length of the rope or slinky or whatever it is, increases by multiples of half a wavelength. If the frequency stays the same, but you increase or decrease by half a wavelength, you just add or subtract nodes on the standing wave, as you can see by A, B, and C here. This is also something we talk about in class. And this last part is just a little introduction here. We will be going over this in class if we haven't done it already. The same with the last part of your notes, which talks about bow waves and sonic booms. But we're going to talk about the Doppler effect. I've even got a song about the Doppler effect. So we're going to leave it here, and this is just a little taste of what you have to look forward to in class to learn about the Doppler effect, how Doppler radar works, how why Sheldon's costume is the way it is on the Big Bang Theory, his Doppler effect costume. So we'll be talking about all this stuff in class, and if any of this is unclear, come to class with questions, rewatch this, read your book, enjoy learning about waves. Until next time, may the mass times acceleration be with you.